Okay, hello, this is a video where I work out the 12 questions that I received taking Pop Quiz 5. That's currently open. That is designed to prepare you for Exam 2A and most of Exam 2B. All right, so let's start with a question that is from Unit 1, Module 3. And so we have a formula, our problem where we have 52.8 grams of C2H7F3. And so the first thing we want to realize is we have for every 1 mole of C2H7F3, there is a total of 88 grams, right? So we can compute the molecular mass and we get 88 grams. That allows us to set up our ratios where the molecular mass, so the first one is the only one that might change because Y moles over 1 mole, Z particles over 6.02 times 10 to the 23rd. And so the idea is that if we're given any formula, we could find the molecular mass and put it in there. And then if we're given X, we can find Y or Z. And if we're given Z, we can find X or Y. So in this problem, we want to find Z number of particles, given X number of grams. Okay, so X grams is 52.8, and we put this in the formula. We put 88 grams in for the molecular mass. We want to solve for Z particles, and if we do that, we multiply both sides by 6.02 times 10 to the 23rd to get Z by itself. And the answer is 3.6 times 10 to the 23rd, which we would put that value 3.6 into the box because we want to put the answer in units of times 10 to the 23. It's just that the formatting in D2L is pretty rough and won't accept scientific notation. If we wanted to do this using conversion factors, it's pretty straightforward. We start with the given information, 52.8 grams. We have to first convert to moles using the molecular mass. And then we use Avogadro's number to cancel out the moles. And if we do that, we get the same number. So depending on how you want to do it, conversion factors or using ratio methods, the main thing is you have to first find the molecular mass and then use it to either calculate particles from grams or calculate grams from particles, which we'll do next. Okay, so in this question, this is the other type of question in Unit 1, Module 3B. We're given a certain number of molecules or particles, and what are the grams? So we set up our ratio here, X grams, Y moles over 1 mole, Z particles over Avogadro's number. Step 1 is calculating the molecular mass. And the formula is C4Cl6F6. All right, so we do that. It's 375 grams per mole. So we have X grams over 375 is equal to 2.6 times 10 to the 22. That's Z. So we're given Z in this problem. 6.2 times 10 to the 23rd. And now we solve for X. X grams will be 375 grams times 2.6 times 10 to the 22 over 6.02 times 10 to the 23rd, or 16.2 grams. Now, we could also do this with conversion factors. So we do this with conversion factors, and we start with 2.6 times 10. You always start with the information given, and then you have to cancel. Right? Usually what you have to do is you have to convert to moles, and you do that by canceling out the units. So we need molecules in the denominator, which is Avogadro's number. Now we have moles. We then use the molecular mass to get to the grams, and moles cancel, and we get the same answer. So either way, depending on how you do it, you just want to make sure that if you're given X, you can find Z. If you find Z, you can find X. Those are the two types of problems you'll see on our exam and homework. Okay, so moving into Unit 1, Module 4, we got this question. So let's take a look at what it's asking. We have 11 electrons, 11 protons, and 13 neutrons. Well, 11 protons are really important. Why? Because this is the identity. The periodic table is set up so that the elements are all given unique number of protons. So 11 protons is sodium. Now the total charge is the number of protons minus the number of electrons. And in this case, these are equal. 11 electrons and 11 protons. That means the overall charge here is neutral, or 0. The total mass is the sum of the number of protons plus the number of neutrons. It's called atomic number, and it's given A. So when we look at this symbol, this is how it's written. A is given as a superscript on the left-hand side. Z, number of protons, is given as a subscript on the left-hand side. And the total charge is on the right-hand side. So to summarize, A is the total mass, sum of protons and neutrons. Z is the number of protons. X is the element identity. And 0 there is the total charge. The total charge is the difference between number of protons and the number of electrons. Okay, so doing that, the total mass is 24, and we would pick sodium 24 as the answer. All right, the next type of question in Unit 1, Module 4 is the mass percents given a mass spectrum. Okay, so remember, the mass spectrum at the moment is only conveying to us the total mass. And we find the total mass by looking at the highest mass peak in the x-axis. So we just go over, it doesn't have to be the tallest peak, but it just has to be a peak farthest to the right. We call that the molecular mass ion. Okay, so our mass is either 64 or 65. Pretty much get the same answer using either number. All right, so we're going to do the molecular mass method first, where we take the molecular mass and we multiply by the percent of each element to get the number of grams contributing to the molecular mass for each element. So we got the 0.375 by taking the percent carbon and dividing by 100. That gives us 24 grams of carbon. Do the same thing for hydrogen. Get 2 grams of hydrogen. Remember, that's percent hydrogen divided by 100. Times 65. And we do the same thing for fluorine. We get 38 grams of fluorine. Now, to obtain the integer contributions, we have to divide by their atomic masses. And if we do that, we see that we get a ratio of 2 carbons, 2 hydrogens, and 2 fluorines, which we can construct the molecular formula from this information by doing C2H2F2. The question didn't ask for the molecular formula. It's underlined and in bold that we want the empirical formula. The way we get the empirical formula is if the coefficients share a common multiple, you can reduce it. So empirical means irreducible. But C2H2F2 is clearly reducible, because if we divide by 2, we could get CHF, and that would be the empirical formula. So the empirical formula is CHF, the molecular formula is C2H2F2. Now the second way shown in class was if we assume a 100-gram sample, then we can use the percents to obtain the amount of grams contributing by each element. So we have 37.51 grams as carbon, which we could then convert to moles. We have 100 gram sample, 3.15 grams is hydrogen, which we can convert that to moles. And then in the 100-gram sample, we have 59%, 0.953, which gives us 59.34 grams of fluorine. So So this is the principal use because you can convert the percents directly into masses this way. You divide by the atomic mass and you say for every 100 grams, you have 3.15 moles of each of these elements. What we do now is we divide by the contribution of the lowest number, and so they happen to be all the same in this problem, but if it were different, you would always pick the lowest one, and then what we get are the integer, the empirical integers relationship. So the empirical formula now, the 100-gram method is also called the empirical formula method, because you can always determine the empirical formula using this. And so we see C1H1F1. But to get, in this method, to get to the molecular formula, you have to know the molecular mass. And why is that? Because the empirical formula, the empirical mass is only 32. But when we look at the mass spectrum, the molecular mass is 64. Because of that, we have to multiply by 2. So to obtain the molecular formula, although not asked in this problem, but just for completion, we would have to multiply each of the coefficients by 2, and that would give us the molecular formula of C2H2F2. So so this is a summary of the two methods. Both of them give you the empirical formula and molecular formula. It's just which one do you get first. In the molecular formula method, you get the molecular formula first, and you have to then divide by a multiple. In the 100-gram sample method, you get the empirical formula first, and then you have to find whatever factor is necessary to get to the molecular mass. Okay, so this is Unit 2, Module 1. It involves light. So let's take a look at it. We're given a certain wavelength that we want to know how much energy is in a mole of these photons. So 422 nanometers, this is visible light. And these are conversion factors. 1 nanometer is 10 to the minus 9 meters, or 10 to the 9 nanometers is 1 meter, right? So they're the same, just depending on what you have one of. And so, as we mentioned in class, we can use a substitution here. N is the same as 10 to the minus 9 meters. So we can write this as 422 times 10 to the minus 9 meters. That's pretty straightforward. Or we can use the conversion factor using the second one. For every 1 meter, there's 10 to the 9 nanometers. And we get 422 times 10 to the minus 9. Which is the same as 4.22 times 10 to the minus 7. Same answer, just how you go about doing the conversion factor. Okay, so let's get the energy for mole of photons. Well, that's just going to be the energy per photon times Avogadro's number. Times Avogadro's number divided by 1,000 to get into kilojoules, because the energy per photon's in joules. So what we have to do is get it into kilojoules. That's what's requested. And so then when we do that, we can simplify this to just change Avogadro's number to 6 times 10 to the 20. And that takes care of the 1,000 joules in the denominator and will help us avoid any mistakes of either multiplying by 1,000 or something strange happening. So if we do that, put in our numbers, so H is 6.626 times 10 to the minus 34 joule seconds. C is 3 times 10 to the 8 meters per second. And now we just put in our wavelength, 4.22 times 10 to the minus 7. And we're going to multiply all this 6 times 10 to the 20. The two values I obtained was 4.7 times 10 to the minus 19. That's the number of joules per photons. Times 6.02 times 10 to the 20. When you multiply these two together, I get 283 kilojoules per mole, which would give me option D. Okay, so you want to make sure that you can do this calculation error-free, a reasonable amount of time, first finding the right wavelength, then using this formula. You wouldn't want to pick option C because it has that times 10 to the 5th there, which is wrong. Okay, so now looking at the model of emission and absorption, we are given an emission spectrum, and we want to know which energy diagram best describes it. Okay, so emission, first let's look at what emission means. Emission means that you have an outer orbit electron. Okay, so inner orbit, outer orbit, and we have an electron in it, right? There's our electron, and it's going from this outer orbit at high potential energy and low kinetic energy, and it's coming down, right? It's radiating down, and so all emission spectra energy diagrams must be pointing down. Okay, so that's the key. And then through this process emits a photon, right? So that's why it's called emission. So all emission points down. All right, so now let's take a look at the relative Roman numerals here. So Roman numeral 1, the lambda 1 is lower than lambda 2, and lambda 3 is the longest, right? It's the biggest value of lambda, which means energy 1 is greatest, energy 2 is the next, and then the lowest energy is energy 3 because of the inverse relationship between energy and wavelength. If we were looking at the arrow length based on this relationship, Roman numeral 1 would have the longest arrow because it's the highest energy. The energy 2 would be a little bit shorter, and then the shortest arrow would be energy 3, primarily because it has the lowest energy. So energy is proportional to arrow length. Okay, so the lowest lambda is the longest arrow and the highest energy. Whoops. Highest energy. Okay, so what does that mean? That means E1 has to have the longest energy and E3 the lowest, and the one that represents that best is C. Okay, so here we're given a problem, and this particular picture comes up a lot. It's from a test bank, but this particular question is asking about which orbit has the electron moving the slowest or has the lowest kinetic energy, right? That's really the same statement. Moving the slowest has the lowest kinetic energy. Okay, so the model is that we have a planetary model, kind of, where the electrons are in these orbits. The electrons here in the inner orbit, that's the inner orbit, and these are all the possible values that the electron can be in. It can't be in orbit 1.5, it can't be in orbit 1.1, it's got to be in these 1, 2, 3, 4 orbits. And what we're talking about is the possibility of comparing the n equals 1 versus n equals 4, right? So we're looking at the slowest. It's either going to be n equals 1 or n equals 4. And so what we talked about is in the outer orbit, right? This has the highest potential energy because the electron is the farthest away from the nucleus. The electron and proton are attracted to each other. This attraction has a minimum value, meaning like the maximum attraction has the lowest potential energy. When that happens when they're closer. As you pull the electron farther and farther away from the proton, the potential energy goes up until it completely removes the electron. It goes out to an infinite orbit. In that case, the potential energy is 0. So anytime the electron goes farther out into an outer orbit, potential energy goes up. Kinetic energy is a different story. The lowest kinetic energy, the lowest speed, comes from the orbit, the maximum orbit. So this is a property of waves in the electron. So the greater the volume the wave is in, the electron wave, the greater the volume, the lower the kinetic energy. So in this case, speed or kinetic energy times orbital volume is a constant. That means that the bigger the volume, the slower the speed. And that's what we've been asked to ask. That's what we've been asked to find. So when you're at n equals 4, right? The n equals 4 is the biggest orbit. You have the highest potential energy. You have the highest potential energy, but you have the lowest kinetic energy. And you have them for this reason. There's a couple more problems in this video regarding this topic, and so we'll cover more details about that coming up. All right, so this question is about relative energies using different wavelength values. So first, one graph is in nanometers. That's a pretty small lambda. This is in reciprocal centimeters, wave number. So it says centimeters to the -1. That means lambda is in centimeters. So anytime you see some distance, you have to put it into the unit of distance. So this would be the reciprocal. And so let's take a look at what we see. Okay, so the biggest lambda is going to be the smallest frequency. So when we see these three pictures, it's going to look something like this. So we're really trying to just find out what is the shortest lambda, what's the largest lambda. Well, it should be pretty clear that the shortest lambda has to be nanometers. It's the smallest unit, nanometers. Centimeters are big compared to nanometers. So we would pick the little wiggly line as Roman numeral 1, right? And that's true for options A and C. But now we have to go and turn our attention to, does 2 have the longest wavelength or does 2 have the shorter wavelength? All right, so let's take a look at that. So the wave number is 1 over lambda, right? So that means 2 is 1 over 3,000 versus 3, which is 1 over 1,500. So the 1 over 3,000 is the smaller wavelength. 1 over 1,500 is the longer wavelength. And so that's why we would put the ordering like this. 3 must be the longest wavelength. It is the, when you take 1 over 1,500, it is a much bigger value than 1 over 3,000. And we're going to see this is characteristic of wave number. It's very similar to frequency, meaning that the lower the wave number, the lower the frequency, and the lower the energy. So that's why we would pick 2 as the, so 3 to be the longest wavelength, because it's definitely the lowest energy of the 2. All right, so in this problem, you're given a visible light spectrum, okay, absorption. So this is the visible light, electronic, has to be electronic because it's visible light. Remember, visible light is between 400 and 700 nanometers, but all electronic transitions are pretty much going to be any nanometers below 700. If the nanometers are above 700, you're in the infrared, and that's vibration, right? So that's so that would be the last two selections, vibrational, if the wavelength was above 700. But in this case, it's below 700, so we know we're dealing with electronic. And now, how do we know what's happening? Well, this has to do with the model of absorption. So the model of absorption is energy comes in via a photon, absorbed light or energy, and we're taking an inner orbit electron to an outer orbit electron. So all the arrows for absorption have to be pointing up, right? They have to be pointing up. And in this case, potential energy is going up because the electron is now farther from the nucleus. Kinetic energy has to be going down because now the electron is in a bigger orbit, and that reduces the speed. Now, oftentimes we ask questions about total energy, and so students often may think, oh, well, potential energy goes up, kinetic energy goes down. There's no change in total energy, but that would be wrong. the change in potential energy is much bigger than the change in kinetic energy. And how do we know that? We know that because we've just absorbed energy in the system by a photon. That's what absorption is that's what it's indicating. So we've absorbed energy. Total energy has gone up because we absorbed energy. So if energy is absorbed, the total energy goes up. And a good way to remember this is the total energy always tracks with the change in potential energy, because that term is the major term in the analysis. Okay, so this is another arrows and connecting it to energy diagrams. So let's take a look at that. So Roman numeral 1, Roman numeral 2, 3, and 4 are all emission. That means they have to be pointing down. 5 and 6 are absorption, so they have to be pointing up. And we start looking at the rankings here. Then energy of Roman numeral 1, the wavelength is longer, then 2, then 3, then 4. 4 is the shortest, smallest value. That means we can rank the energy this way. And also that means the arrows would look like that in terms of their length. The lowest energy has the smallest arrow. The highest energy has the biggest arrow. When we look at our 5 and 6 here, 5 has the lowest wavelength, so it's got the longest, the greatest energy. 6 is a longer wavelength, and so it has a lower energy. So in the absorptions, 5 has to be the longest arrow, and 6 has to be the shortest pointing up arrow. Well, the first thing we can do is look and say, well, which one of these has the smallest Roman numeral 1 pointing down? Because that's got to be correct. And if we do that, we see there's two choices here. That's these two. The others are showing one in different ways, are pointing up, right? So that's wrong. So you can't have 1, 2, 3, and 4 pointing up. They have to be pointing down, and Roman numeral 1 has to be the shortest. So how do we distinguish the two? Because after that, it looks like the ordering is correct in emission. It has to do with the 5 and 6. So 5 is the longest arrow pointing up, 6 is shorter. And so that would make, okay, so in the top one, the 6th one is longest, and in the one I'm writing in now, 5 is the longest and 6 is the shortest. So that's going to, so this one is incorrect because it's showing 6 as the longer arrow, and but that can't be because it has the longest wavelength. So the shortest wavelength, longest arrow for absorption would be 5, and that gives us this option. Okay, so the final question I was given in the quiz was another calculate the kilojoules per mole. So I'll do this fairly quickly. Energy is energy per photon times our 6 times 10 to the 20. So we put this in the formula. H 6 times 10 to the minus 34 times 3 times 10 to the 8. We're given the wavelength. That's nice. 1.2 times 10 to the minus 6. We multiply all this, 6 times 10 to the 20, and we get 99.7 kilojoules per mole, and that's one of the options. So if I had to summarize the types of questions we are going to be asking you, we're going to have Unit 1, Module 3, grams to particles, particles to grams. Right? So we did 2 examples of that. You want to make sure you know how to do it. Unit 1, Module 4, we saw a couple different questions, one in which there was the sort of navigating the atomic representation, total mass, number of protons, total charge, and we saw percent mass given a percent mass of different elements, and we're given a mass spectrum, and the question was asking find the empirical formula, find the molecular formula based on that work. And then the final sets of problems that were given involved wavelength, frequency, energy, joules per photon, energy, kilojoules per mole of photons. We also have the model in which we are. Okay, so we have the atomic emission and absorption model. And in that case, the potential energy, kinetic energy was discussed, how changes occur, and that the nanometers are usually electronic. Any nanometers less than 700. Any wavelength greater than 700 or micrometers or reciprocal centimeters are going to be in the infrared. Those are going to be vibrations, different units there. And rotation is in the gigahertz, which we didn't really talk about in this video. We didn't receive any questions on that, but those would be the different regions that you would be responsible for. Okay, I hope this helps put into focus what exam 2A will be and what a majority of exam 2B will contain.